Hello everyone. This is Qi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Hello everyone. Back to our Deep Learning course. Today we start Chapter 2, Neural Network Foundation 1. I'm Qi Jiaming. Let's jump into Neural Network Basics, the core of deep learning. First, our learning objectives for this chapter master 4 key points. First, structures of MP neuron perceptron and multilayer perceptron. Second, definitions and differences of sigmoid, tanh, ReLU. Third, backpropagation principle. Fourth, handling neural network overfitting. Keep these in mind. Now we're in part 2.1. We'll start with the most basic unit of neural networks, the MP neuron model. Proposed in 1943 by McCulloch and Pitts, it's the first math model abstracting biological neurons. It's a multi-input, single-output unit. Working steps: take n inputs, weight, sum, pass-through activation function output. Note, its parameters are set manually. Proposed in 1957 by Rosenblatt, it's a single-layer neural network. Goal: build linear hyperplanes to solve linear separable problems. Unlike MP, its parameters update automatically via training. Prep samples calc output, adjust params if error repeat till error is small. The perceptron's output rule: if b plus w sub 1 x plus w sub 2 x sub 1 is less than or equal to 0, y equals 1. If is greater than 0, y follows the activation function. In short, y equals f b plus weighted sum of inputs. That's its core math logic. MLP adds hidden layers between input and output layers. This lets it handle nonlinear problems, a big step from single-layer perceptrons. Key points: count layers excluding input. For example, 1 hidden plus 1 output equals 2 layers. It's also fully connected. Adjacent layers neurons connect entirely. Next, part 2.2, activation functions, critical for neural networks to learn nonlinearity. An activation function is a nonlinear transformation. It breaks linear combinations of linear combinations, making multi-layer networks more powerful. Common ones: sigmoid, tanh, ReLU. Others like leaky ReLU exist, but we focus on the first three. Formula: 1 over 1 plus e to the negative x, maps inputs to 0 to 1 TensorFlow, code, TF. NN. Sigmoid x. For tensor 1, 2, 2, 0, output is roughly 0.73, 0.88, 0.88, 0.5. Next is the tanh activation function, also known as the hyperbolic tangent function. Its mathematical formula is tanh x equals e to the power of x minus e to the power of negative x divided by e to the power of x plus e to the power of negative x, which can also be written as 1 minus e to the power of negative 2x divided by 1 plus e to the power of negative 2x. Both forms are equivalent. Unlike sigmoid, the tanh function maps input values to the range -1, 1, which is a key difference. In TensorFlow, the implementation code is TF. NN. tanh x, name equals none. Let's use the same input tensor as before, t equals TF. Constant 1, 2, 2, 0, TF. Float 32. When we compute result equals TF. NN. tanh t and run the session, the output will be 0.76159420, 0.96402760, 0.96402760. You can see that the outputs here range from -1 to 1, which aligns with the tanh function's value range. The page also includes graphs of the tanh function, primitive, and its derivative, showing how its shape differs from sigmoid. The last common activation function we'll cover is ReLU, which stands for rectified linear unit. Its mathematical formula is simple: ReLU x equals max x 0. This means if the input x is positive, the output is x itself. If x is non-positive, the output is 0. In TensorFlow, we use TF. NN. ReLU x name equals none to implement it. Let's test it with the same tensor t equals TF. Constant 1, 2, 2, 0, TF. Float 32. Computing result equals TF float 32. NN. ReLU t and running the session gives the output, January the 2nd, 0. Exactly as the formula suggests, positive values 1, 2, 2 stay the same, and the non-positive value 0 remains 0. An important point to note, as mentioned on the page, the ReLU function has been shown to provide better performance results compared to the sigmoid and tanh functions in many deep learning tasks, which is why it's widely used in modern neural networks. The page also includes graphs of the ReLU function and its derivative, highlighting its simple yet effective nonlinear characteristic.